In the previous videos, we have defined cylindrical and orthogonal coordinates and talked about integrals. In this part, we will continue and talk about derivatives. Before we start, I want to say a few words about this topic though. We have already seen that all operations involving the Nabla operator will be different when we move to cylindrical coordinates. And now it's time to explain why this is the case. Note that when you use this in the future, you will simply look up the expressions in the formula sheet. The purpose of this video is to show you the derivations of the equations you will find in your formula sheet. The idea is to give you a better understanding of how orthogonal coordinate systems work. But the things we do here is something that we do once, and then we use our final expressions in the future. With that, let's get started. First, let us recall our unit vectors rp hat and phi hat in cylindrical coordinates. Note that both are dependent on the angle phi. This means that we get a derivative with respect to phi. We can distribute the derivative operator. The derivative of cosinus phi is minus sinus phi. And the derivative of sinus phi is cosinus phi. This means that we can identify the rp hat d phi as the unit vector phi hat. Let us repeat the same steps for phi hat. Distribute. The derivative of sinus phi is cosinus phi. And the derivative of cosinus phi is minus sinus phi. And we can identify d phi hat d phi as minus rp hat. It's very important to remember that we have these derivatives for the unit vectors, as this is different from Cartesian coordinates where the unit vectors are constant. To demonstrate how this is important, let us take the time derivative of the position vector. Assume that the position vector indicates the position of an object, the time derivative will give the velocity of the object. Distribute the derivative operator. As rp hat can vary with angle, we have to apply the product rule for differentiation here. Use the chain rule by multiplying and dividing with the d phi. And insert that the rp hat d phi is phi hat. This is the expression for the velocity of the object in cylindrical coordinates. The first term represents a change in radial position. In the second term, d phi dt is the angular speed. Hence, this is our classical equation for rotating motion, that the velocity from rotation is the radius times the angular speed in the tangential direction. The final term is the velocity in the z direction, just as we are used to from Cartesian coordinates. Let's take the time derivative once more and calculate the acceleration as well. Distribute the derivative. Apply the product rule. Use the chain rule by multiplying and dividing with d phi. And insert that the rp hat d phi is phi hat. Apply the product rule. These two are the same. Use the chain rule. and insert that the phi is minus rp hat. Combine these into a square. This is the acceleration in cylindrical coordinates. This is commonly used for rotating coordinate systems. We can identify the second term as the Coriolis acceleration. The next term is the centripetal acceleration. And the next one is called the Euler term. If you study mechanics, you will likely come in contact with these again. Next up, we'll talk about the gradient. First, let us do some recap of Cartesian coordinates. Assume that you have a vector A. We can express this vector by its x component ax and y component ay. Now let's say we have two other Cartesian unit vectors, u hat and v hat. We can now express A in terms of AU and AV instead. Let us assume that vector A is the gradient of some scalar function f. To calculate the gradient, you will start by defining f of x and y at the position of the vector A. To get the x component, you will take one small step delta x in the x direction. Then, per definition of the partial derivative, we take the difference between these points and divide by the step delta x. And then let delta x go to 0. To get the y component, we take the small step delta y in the y direction instead. This gives us our two components for the gradient. Let's say we want to use our coordinates u and v instead. To get the u component of the gradient, you have to take the small step delta u in the u direction. And to get the v component of the gradient, we have to take the small step delta v in the v direction. The vector A is still the same vector in both cases. We have just expressed it either in the xy coordinates or in the uv coordinates. Now let's say that u hat and v hat actually are our rp hat and phi hat from cylindrical coordinates. We can therefore say that f is a function of rp and phi. We can also claim that since u hat and rp hat are the same vector, and the vector A should be the same independent of which coordinate system we use, the coefficient AU should be the same as the coefficient ARP. We can also rename the small step in the radial direction using RP and phi instead. And insert these into the definition of the derivative. Remember, it's still exactly the same points, just with new names. We can also rewrite delta U as delta RP. And insert this into the definition of the partial derivative. As this is the definition of the partial derivative, let us write it using the partial derivative instead. Let us continue with the phi component, which will be slightly more complicated. First, since phi hat is the same as v hat, the coefficients have to be the same to get the same vector. Next, rename the small step in the phi direction using RP and phi. Once again, we are still using exactly the same points. Use our new names in the definition. However, as we step in delta phi, we have to count for what the length delta v actually is. We have mentioned several times in the earlier videos that a small step delta phi gives the actual length rp delta phi. Hence, we should replace delta v with rp delta phi here. We can move 1 over rp in front and identify this part as the partial derivative with respect to phi. Finally, let's update the expression for a using these new coefficients. What we get is that to ensure that we have the same gradient independent of coordinate system, we need to add the 1 over rp in front of the partial derivative with respect to phi. If we use cylindrical coordinates in 3D, the z direction is the same as for Cartesian coordinates. We will continue with the gradient a bit more and talk about the general case for orthogonal coordinate systems. Change the unit vector names to general names u1 hat and u2 hat. Let's bring back what we derived for general orthogonal coordinates in the previous videos. We call the point f of u1 and u2. This will be the small step in u1. And this is our small step in u2. This would be a u2 in our general coordinate systems. Update with the new names. In the general case, a small step in u1 will move a distance h1 delta u1, where h1 is our scaling factor. And a small step in u2 will move the actual distance h2 delta u2. This means that rp is our scaling factor h2 and delta phi is our delta u2 for general orthogonal coordinates. The general case is therefore that one should include a 1 over h factor in each direction for the gradient. A quick note on the directional derivative for scalars. It is simply the dot product with the gradient as before. All you need to think about is to include the updated expressions for the gradient. We can still talk about the gradient as an operator simply by removing f from this equation. Now, things will get a bit harder as we're going to talk about the gradient of a vector field. First, consider the following example. Let v be a constant in the phi hat direction. We want to calculate the vector gradient with respect to the two directions rp hat and phi hat. Just like for the ordinary gradient, we will assume that if we have a Cartesian coordinate systems with the same unit vectors, we should have the same vector gradient. If we consider the partial derivative with respect to rp, we will be moving in this radial direction. This is the easy direction, as both cylindrical coordinates and our Cartesian coordinate system with the unit vectors in the same directions consider the vector field to be constant when moving in this direction. The tricky part is the tangential direction. For a Cartesian coordinate system with fixed unit vectors, we would be moving along this line for the derivative. Note that the direction of the vector field changes along the line. The case is similar if we change the direction of the vector field to be in the radial direction. Everything is constant if we move in the radial direction. If we move in the phi hat direction though, we can see that the vector field changes direction along the line. Note, however, that the vector field is a constant times the unit vector. The derivative of a constant is 0. The fact that the vector field still changes value when we move in the phi hat direction is because we have a phi dependence in our unit vectors, which we must account for in some way. To do this mathematical, let's first remind us that the vector gradient can be written as a dyadic product. First, I'm going to change how we write dyadic products a bit though, as I think the matrix notation is confusing here. Instead of using matrices, let us write our vectors using unit vectors. This means that we can write the dyadic product as a sum of 9 terms, each with a dyadic product of 2 unit vectors. Next, let's insert a gradient operator instead of the vector a. This is okay when we use the denominator layout for the vector gradient. A should be replaced with a gradient. Here, I will show it in Cartesian coordinates first, just to illustrate the notation. Replace the coefficients for the dyadic product as well. This is what the vector gradient would look like in Cartesian coordinates, using our new notation. Let's go back to our dyadic product again. And change to cylindrical coordinates. Now we will repeat the steps again and replace a with the gradient operator. Insert a gradient in cylindrical coordinates here. And update the dyadic product. On the first row, it is only the coefficients b that can depend on Rp. On the third row, it's also only the coefficients that depend on z. And z hat is also constant, hence only bz depends on phi. Now comes the complicated ones. We know that Rp hat is a function of phi, hence we need to apply the product rule here. The Rp hat of phi is phi hat. Again, phi hat depends on phi, and we need the product rule. The phi hat of phi is minus Rp hat. Collect the terms belonging to the same unit vectors. This is the final result. Now we can return to matrix notation if you desire. You can see that there will be extra terms due to that the unit vectors are functions of phi. We will not derive any expressions for the general orthogonal coordinates here, as those would be complicated. Instead, you can use the same method as we used here to derive the vector gradient for other coordinate systems as well. A related topic to the vector gradient is the directional derivative of a vector in cylindrical coordinates. Let's say we want to calculate v dot nabla b, where nabla b is our vector gradient. This will simply be a matrix multiplication between v and the vector gradient. Start with the first column. Continue with the second column. And the third column. This is the final result for v dot nabla b, which is the directional derivative multiplied by the length of v. In fluid mechanics, this will appear in Navier-Stokes equations with b equals v. The most common operations for vectors are the divergence and the curl. Similar to what we have learned before, the divergence is the sum of the diagonal elements of the vector gradient. The curl is given by the off-diagonal elements. Start with these for the r hat contribution. These give the phi hat contribution. And these the z hat contribution. Hence, once we had derived the vector gradient, we basically got the directional derivative, the divergence, and the curl. We will continue and focus on the divergence and the curl, as it is possible to derive general expressions for this. Start by the expression for the divergence, which we can derive from Gauss' theorem. Using the divergence version, Gauss' theorem states that the volume integral over the divergence equals the surface integral of n hat dot the vector integrated over the closed surface of the volume. Define the vector b using a general orthogonal coordinate system. We can visualize these in 2D by drawing a small volume element. The lower corner is b of u1, u2, and u3, which gives the following coordinates for the other corners. Use the general expression that the distance, if we take a small step in the u1 coordinate, is h1 delta u. Here, h1 is the same scaling factor that we have used multiple times in these videos. Similarly, the distance in the u2 direction when we take a small step delta u2 is h2 delta u2. As you visually can see, the length in the u2 direction varies between the size of the volume. Hence, for the first scaling factor, add that h2 is the value at the base position u1, u2, and u3. And in the second, h2 is the value when we're taking a small step delta u1. For future use, I have added delta u1 in the index of the name, so we can drop the arguments later. For the general case, we should do the same for the u1 direction. This is the base position. And this is when we have added the step delta u2. Again, we'll add delta u2 to the index. Now, let us use Gauss' theorem. Start with the volume integral. If we assume that the volume is small, the divergence is approximately constant. Hence, this simply becomes the volume times the divergence. The volume is given by the product of the length of the sides. Here we can neglect that h changes if the step is small. Hence, the volume is h1, h2, h3, delta u1, delta u2, and delta u3, just as our volume element for triple integrals. Let's divide by the volume to get the divergence as the left-hand side. Next up, we need to calculate the surface integral. Let's start with the u1 direction. Start with the orange surface, which has normal vector in the same direction as u1 hat. As the area is small, we can approximate it by the vector value b at this point, multiplied by the area. The area is the product of the length of the sides. We need to include that the scaling factors are evaluated at u1 plus delta u1, which gives the following. Let's continue and move to the opposite side, where the normal vector is in the negative u1 hat direction, which gives a minus. We multiply with b, with the area again. Now everything is at the base position u1. Multiply and divide by delta u1. All terms include delta u2 and delta u3. This can be identified as the partial derivative. Note, however, that all b1, h2 and h3 are evaluated at u1 plus delta u1. This means that the derivative will include all these three. It is common to place b1 last. The other two directions will follow the same pattern. Hence, I will just write out the results. Let's divide the expression with h1, h2, h3, delta u1, delta u2, delta u3 to get the divergence. We can see that all delta terms will cancel. Now we can write it as the divergence. This is the general expression for the divergence in an orthogonal coordinate system. We can do a similar derivation for the curl using Stokes' theorem. Here I will only show the u3 component. Stokes' theorem states that the surface integral over the dot product between the curl and the normal vector equals the closed line integral around the boundary of the surface. This means that we can consider our drawing a surface in the u1, u2 plane. The blue line is the boundary. The line integral should be counterclockwise according to mathematical standard. If we assume that the surface is small, the curl is approximately constant. And this integral can be written as the multiplication with the surface area. The surface area in orthogonal coordinates is simply the dot product of the two sides. We can divide by the surface area to get a u3 component of the curl of B. Continue and calculate the boundary integral. Start with the orange segment. If we assume that it is small, we can insert the value times the length. Any of the two b values will work. This curve is in the u2 direction. Hence, the dot product gives the b2 component. Continue with the next segment. Any of these values for b times the length will work. As the curve is in the negative u1 direction, we insert a minus and the u1 component of b. Continue with the next segment, which is the negative u2 direction. Hence we get minus u2 component of b times the length. Finally, the last segment, which is in a positive u1 direction. Insert b1 times the length. Let these two swap places. Multiply and divide by delta u1. Place delta u2 in front of the fraction. This can be identified as the partial derivative with respect to u1. Note that the derivative includes both b and h. We repeat for this term. Multiply and divide by delta u2. Place delta u1 in front. And identify as the partial derivative with respect to u2. Delta U1, delta U2 is a common factor. Divide by H1, H2, delta U1, delta U2 to get the Z component of the curl. These will cancel. Write this as the curl instead. The common form is to write B last here. If we want the other two directions, they will be given by similar expressions. Just update the indices. This is the general expression for the curl in an orthogonal coordinate system. Let us demonstrate that these give the same equations for cylindrical coordinates. All we need to know are the three scaling factors h, which we will insert into the expressions. First, we remove all that are 1. Then we insert Rp as h phi. Distribute 1 over Rp. Rp is not the function of Z and can be placed before d to z. Rp over Rp is 1. Distribute 1 over Rp. If we were to use the product rule, this term would become the two terms in our old expression for the curl. Hence, you can see that we get the same expression as we got from the vector gradient. Let us show the expression for the divergence as well. Start by removing h1 and h3 as they are 1. And set h phi as Rp. Distribute 1 over Rp. Rp is not the function of Z. And we can remove Rp over Rp. Again, if we would apply the product rule, this term becomes the two selected terms from our old expression for the divergence. Hence, we can conclude that we get the same expression using the general equation as from the vector gradient. Moving to our next operation, which is a scalar Laplacian. We do this for general orthogonal coordinates, first by recalling the expression for the gradient. Then we can use the general expression for the divergence. And we can insert the gradient as the vector b. Insert each coefficient. The divergence of the gradient is the Laplacian. And we have a general expression for the Laplacian of a scalar as well. Let's insert h values for cylindrical coordinates. Start by removing h1 and h3 as they are 1 and replace h2 with Rp. Distribute 1 over Rp. 1 over Rp is not the function of phi. This can be written as d to the phi squared. RP is not a function of Z. RP over RP can be removed. This can be written as d to the z squared. This is our scalar Laplacian for cylindrical coordinates. Before we cover the Laplacian for a vector, we are going to look at the divergence of a tensor in cylindrical coordinates. Just like the vector gradient, we will only cover cylindrical coordinates here. Let's write the tensor divergence, similar to our matrix multiplication, but we use the format with the unit vectors on each term, the same way as we did for the vector gradient. This is because we have to take the derivative of the unit vectors. I want you to recall the associative property of the dyadic product, which we can do the dot product first. This means that if you have rp hat dot the dyadic product of rp hat and c, this is rp hat dot rp hat times c. As rp hat dot rp hat is 1, this would just be c. If you have rp hat dot the dyadic product of phi hat and c, this is the same as rp hat dot phi hat times c. As rp hat dot phi hat is 0, this is 0. These are the ones you use when doing the dot product with a tensor using the unit vector notation. We also need to remember that the rp hat the phi is phi hat, and the phi hat the phi is minus rp hat. Let us collect all terms starting with rp hat. Collect all phi hat terms as well. And the z hat terms. Let us do this calculation part by part. Start with rp hat ddrp dot the tensor. As no unit vector depends on rp, it will only be those terms that start with rp hat that will give a contribution. After the dot product, we get the following. Distribute the partial derivative. Let's continue with a complicated expression, which we get from phi hat 1 over rp times d phi dot the tensor. This one is complicated due to the phi dependence of our unit vectors. Start by distributing phi hat and the derivative. Then apply the product rule. We can use the associative property for the dyadic products here. As rp hat dot phi hat is 0, the second part will be 0. The rp hat the phi is phi hat. Use the associative property. Phi hat dot phi hat is 1. Use the product rule. The phi hat the phi is minus rp hat. Use the associative property. Phi hat dot rp hat is 0. Use the associative property again. Phi hat dot phi hat is 1. Distribute d phi again. Use the product rule. The RP hat to phi is phi hat. Use the product rule. The phi hat to phi is minus RP hat. For the last row, note that z hat is not the function of phi. Use the associative property. Phi hat dot z hat is 0. Finally, the z hat term, which is the easy one. It is only the last row that will give a contribution, which after the dot product becomes. Distribute the dz. Let us combine the three contributions. Start by collecting all RP hat terms. Then collect all phi hat terms. And collect all z hat terms. This is the final expression for the divergence of a tensor of rank 2. Note that just like for the vector gradient, we get additional terms due to the derivatives of the unit vectors. Let's use this result to calculate the Laplacian of a vector. We do this by inserting the vector gradient as our tensor. All we need to do is insert the values for each of the 9 elements of the vector gradient. Start by inserting this. Continue with this. Distribute. And distribute. These two are the same. Let us recall the Laplacian for a scalar. If we use the product rule, this becomes... Both of these are 1 and can be removed. Note that this part is the scalar Laplacian of the radial component of B. Hence, it's common to write it in terms of this scalar Laplacian to get a shorter expression. Let's continue with the phi direction by inserting these elements from the vector gradient. And insert this. Distribute. And distribute. These are the same. This part is the scalar Laplacian of the phi component of V. Finally, insert the vector gradient elements to these. We can directly identify these as the scalar Laplacian. This will be our final expression for the vector Laplacian. Once again, remember the extra terms we get in the RP and phi directions. This is our final derivation for this video. Let's end with a summary of all our expressions. We had expressions for the directional derivative. We had the gradient of a scalar. We had the divergence of a vector. And we had the curl of a vector. In the future, you can simply use these expressions, and you will likely just look them up in the table of equations. Be aware that these are in the denominator layout for the vector gradient. If you look in a table and see the transpose matrix, they are using the numerator layout instead. Let's do a recap of the first two videos in this series as well. Let's bring back our graphical representation of the position vector and unit vectors in cylindrical coordinates. The position vector is given by the following expression. This means that x is rp cosine phi and y is rp sinus phi. To go from x and y to cylindrical coordinates, rp is given by the Pythagorean theorem. Phi is given by arctan y over x, where you need to add 180 degrees if x is smaller than 0. We can also express rp hat and phi hat in terms of x hat and y hat. Similarly, x hat and y hat can be expressed in terms of rp hat and phi hat. If you need to transform a vector to cylindrical coordinates, use the following formulas. And if you want to transform a vector from cylindrical coordinates to Cartesian coordinates, use the following. When doing line integrals, the small line element s is expressed in terms of the rp, the phi and the z according to this. For surface integrals, we covered the cases where one coordinate is constant and the other two vary on the surface. With a constant radius, this is the surface element. This is commonly used to integrate over the lateral surface of a cylinder. If phi is constant, we get the following. This is used to integrate over a plane at angle phi. Finally, when z is constant, we have the following. This is commonly used to integrate over the ends of a cylinder or an ordinary circle in the xy plane. We also have the volume element for triple integrals that we integrate over the volume of a cylinder. Finally, let's do a summary of general orthogonal coordinates as well. We assume that we use coordinates u1, u2 and u3, and the vector is given using the unit vectors u1 hat, u2 hat and u3 hat. We define the length of the partial derivative of the position vector with respect to ui as the scaling factor hi. And then define the unit vector ui hat as 1 over hi times the partial derivative with respect to ui. In cylindrical coordinates, we have hr is 1, h phi is rp, and hz is 1. If you have a vector given in Cartesian coordinates and want to express it in our general system, use the dot product between the vector and the unit vector. The dot product can be used in the opposite direction as well. When doing line integrals, the small line element ds is given by this. Here, we need to use our scaling factors h to get the correct length. Similarly, for the case where uk is constant and ui and uj varies, we have the surface element. We also have the volume element. Going to derivatives, the gradient is given by. We also have the divergence. And we have the curl. Finally, we have the Laplacian for a scalar. These are all equations we derived for general orthogonal coordinates. We will see another example of how to use these in the next part when we talk about spherical coordinates. This is the end of this block. Thank you.